Symmetry is a property of a figure that we can identify by rotating it, flipping it, or even folding it. So for example, if I try to fold this triangle here like this, we can see that the two halves of the triangle do not perfectly map onto each other. So let's try another fold. This is another version of the same triangle. Now, if I fold it in this direction, we see that the two halves align perfectly. I have found a symmetry of this triangle. This lesson will explore lines of symmetry and rotational symmetry of a figure while we answer the question, how can you identify symmetry in a figure? Reflectional symmetry of a geometric figure is the characteristic of a figure to map onto itself across a line of symmetry. Remember that symmetry is a mapping of a figure, such as this triangle or a piece of the triangle, onto itself. For reflectional symmetry, we think of the number of lines of reflection or lines of symmetry that can be drawn on a figure that would produce a mirror image on either side. Let's consider if we drew a line of symmetry from the vertex A to the midpoint of side CB. Is this a line of reflection? We see that when we fold the triangle across the line connecting the A vertex to the midpoint of the opposite side, so this figure right here, does not give a line of symmetry. The sides are not mirror images of one another. Likewise, the fold of the triangle across the line connecting the vertex B to the midpoint of the opposite side AC does not give a line of symmetry either. These lines are not lines of reflection for this triangle. So what are the criteria for drawing a line of reflection? Well, the number of lines of reflectional symmetry will vary for each geometrical figure. The figure is said to have n-fold reflectional symmetry, where n is the number of lines of symmetry. So n-fold represents the number of lines of reflection that can be drawn on a figure. If a figure has 3-fold reflectional symmetry, for instance, there are 3 lines of reflection that can be drawn on that figure. Let's take a look at the criteria for lines of symmetry. So when crossing from an angle to an angle, a line of symmetry will be an angle bisector of both angles. When crossing from a vertex to a side, the line of symmetry will be an angle bisector of the vertex, and it will be a perpendicular bisector of the side of the figure. And when crossing from a side to a side, then the line of symmetry will be a perpendicular bisector of both sides. So when we work with a geometric figure, such as this triangle, the line of reflectional symmetry should bisect the angles, if originating from a vertex, or be a perpendicular bisector of the side of the figures. If the line of reflectional symmetry cuts through an angle and a side, then the line should bisect the angle and cross through the midpoint of the side. Let's consider the lines of reflectional symmetry for this triangle. We already saw that the lines from the vertices A and B to opposite sides are not lines of symmetry because they do not bisect the angles. But let's consider a line from the vertex C to the midpoint of AB. We can imagine folding the triangle across this line and getting a mirror image on either side, and we see that angle C is bisected. We can again imagine folding the triangle across this line to show symmetry. So this triangle has one fold, reflectional symmetry. What is the reflectional symmetry for trapezoids? Let's consider these two possible types of trapezoids, isosceles trapezoids and right trapezoids. The first trapezoid is isosceles. Which means one set of sides are congruent and the base angles are congruent. So let's use our criteria to try and draw lines of reflectional symmetry. If we try to draw a line vertex to vertex, we will not produce a mirror image on either side across the fold. So let's try vertical or horizontal perpendicular bisectors. Well, a horizontal line will not work because the top of the trapezoid is smaller than the bottom half. So let's try a vertical perpendicular bisector. So we have created a mirror image on either side that we can imagine to fold the trapezoid. So the isosceles trapezoid has one-fold reflectional symmetry. Now let's consider the right trapezoid. We call it a right trapezoid because two angles are right angles. We see that even if we try to draw the vertical line here, like so, it will not be a perpendicular bisector of the top because the angles aren't congruent. So a right trapezoid has no lines of reflectional symmetry. Generally, we do not say zero-fold reflectional symmetry, just that the figure has none. The same would be true for scalene trapezoids that will be discussed in another lesson. Let's consider these regular polygons and their reflectional symmetry. Regular polygons with n sides will have n-fold reflectional symmetry. For example, a 5-sided regular polygon should have a 5-fold reflectional symmetry. Remember, a regular polygon is a polygon that has congruent sides and angles. Let's check to see if the number of lines of reflectional symmetry is equal to the number of sides of a regular polygon. Let's start with the equilateral triangle on the left. We have 3 sides, so there should be 3-fold symmetry. We can draw a line of reflection from one vertex to the opposite side that bisects the angle and the side. This line can be drawn from all 3 vertices. Imagine folding the triangle across each of these lines to create mirror images. So, an equilateral triangle has 3-fold reflectional symmetry. Similarly, the regular hexagon will have 6-fold reflectional symmetry. So let's draw those lines of symmetry. We have one from side to side, vertex to vertex, another vertex to vertex, another vertex to vertex. So we're at 1, 2, 3, 4 so far. One from side to side, and another one from side to side. That leaves us with 6 lines of symmetry. We see that all the lines of reflectional symmetry either bisect the angle and opposite side, or they are perpendicular bisectors of the sides. We are answering the question, how can you identify symmetry in a figure? We just discussed reflectional symmetry and determining lines of reflection, but what about rotational symmetry? For a figure to have rotational symmetry, it must map to itself after undergoing a rotation of a certain degree measure. So consider this hexagon. What if we were to spin or rotate this hexagon about the center of the hexagon 90 degrees, like this? We see that when we rotate the hexagon 90 degrees, the vertices do not line up, so this transformation does not map the hexagon to itself. Well, what if we rotate this hexagon 180 degrees? So we see that the rotated hexagon does map to itself, so this would be an example of rotational symmetry. What else can we say about rotational symmetry?
The rotational symmetry of a geometric figure is the characteristic of a figure to map onto itself through the center of rotation. The number of rotations that map a geometric figure onto itself is called the order of rotational symmetry. The center of rotation is in the middle of the geometric figure, right here. And the rotation will occur for an angle between 0 degrees and 360 degrees, including 360 degrees. I know that's kind of hard to follow, but stay with me. Imagine if we were to rotate this rectangle 360 degrees in the positive direction, which is counterclockwise, until it landed perfectly back onto itself. Every figure has an order of rotational symmetry of at least 1, because we can always rotate 360 degrees to map a figure onto itself. Let's explore what order of rotational symmetry our rectangle has. A 45-degree rotation through the center of rotation does not map the original rectangle back onto itself. That is, it's not in the same position as it started. We can continue to a 90-degree rotation, and this rectangle is now positioned with the longer sides vertical and the shorter sides horizontal, also not rotational symmetry. On to a 180-degree rotation, and what do we have here? The rectangle does map onto itself. Now vertex A is where vertex D used to be, vertex C is where vertex B used to be, and so on. As before, we can go all the way around to a rotation of 360 degrees back to the original position, and it seems there are only 2 rotations that map this rectangle back onto itself. Rotations of 180 degrees and 360 degrees. So, the rectangle has a rotational symmetry of order 2.
Let's consider the order of rotational symmetry for these 2 trapezoids. The first, to the left here, is an isosceles trapezoid, so it has one set of equal sides. We can imagine rotating this trapezoid 45, 90, 180, or 270 degrees through the center of rotation, right here, but it will not map directly onto itself because the 2 bases have different lengths. Thus, the only rotational symmetry would be a full rotation of 360 degrees. So the order of rotation is 1. The same is true of the right trapezoid. It will only map onto itself after a 360-degree rotation. So this also has 1. We usually discuss rotational symmetry of order 2 or higher because an order of 1 only maps onto itself after a full 360 degrees. Let's discuss the rotational symmetry of regular polygons. Consider the equilateral triangle here. We'll call it triangle ABC. We can rotate this triangle at any angle of rotation. Regular polygons with n equal sides will have order n for rotational symmetry. This idea is similar to the fact that regular polygons with n sides will have n-fold reflectional symmetry, if you remember that. So if the triangle has 3 equal sides, it should have order 3 for rotational symmetry. How do we verify this? Well, to find the smallest angle of rotational symmetry, we divide 360 degrees by the number of equal sides, so 3 in this case. And 360 degrees divided by 3 equals 120 degrees. So we find that the smallest angle of rotation is 120 degrees. When we rotate this triangle 120 degrees, let's go ahead and do that really quickly. Click Rotate. We see that it's mapped onto itself. This means that multiples of 120 degrees work. There are 3, so they must be at 120 degrees, 240 degrees, and 360 degrees. So let's try these angles out one more time. So let's try another multiple of 120. Let's try 240 degrees. We'll rotate one more time. So we can see that this triangle rotates 240 degrees, and again, it's mapped onto itself. Now, let's consider this regular hexagon. The order of rotational symmetry is 6 because there are 6 equal sides. So the order of rotational symmetry is equal to 6. The smallest angle of rotational symmetry is 360 degrees divided by the number of equal sides. Well, we know that there are 6 equal sides, so 360 degrees divided by 6, that's 60 degrees. So using this formula, we found that every rotation of 60 degrees will map this hexagon back onto itself. And when we find the order of rotation, we just count positive angles less than or equal to 360 degrees. So when we do that, we have 60 degrees, 120 degrees, 180 degrees, 240 degrees, 300 degrees, and 360 degrees. And remember, we always include the 360 degrees. So notice that we count each time by 60 degrees because that's our smallest angle of rotation. And remember, all multiples of the smallest angle are angles of rotational symmetry. Determine the reflectional and rotational symmetry for the regular pentagon. First, let's find the reflectional symmetry. Recall that a line of reflectional symmetry will be an angle bisector or a perpendicular bisector. For this regular pentagon, it seems as though the possible lines of reflectional symmetry will bisect an angle and then cross through the midpoint of the opposite side. So let's draw these lines of reflection. We'll start at one vertex, travel through the center of rotation, and end up at the midpoint of the opposite side. And we'll do this for every vertex. This will be the third line of reflection, pass through the center of rotation. This is the fourth one. We have one more from this vertex through the center of rotation and passes to the midpoint of the opposite side. So we see that the regular pentagon has five-fold reflectional symmetry. Now let's find the order of rotational symmetry. Because the pentagon has 5 equal sides, the order of rotational symmetry will be 5. The smallest angle of rotational symmetry will be 360 degrees divided by the number of equal sides, so 5. 360 degrees divided by 5 is 72 degrees. So every angle measure that is a multiple of a 72-degree rotation will map the regular pentagon onto itself.